Welcome back. We were discussing flow through a convergent divergent duct. I already gave you what will happen inside, we just have to go into a little more detail. So, I told you already that this particular thing, for it to get into your brains, I have to go into it 3 loops, 4 loops, then only it will get into your brain. We showed you a picture first, then I explained it in one round. We will go through that a little more detail with more plots and figures this time, and probably a animation also. Okay. We are having some convergent divergent duct, and we are saying that we are going to maintain P naught as a fixed value and back pressure Pb back pressure Pb is what we are going to change. We are going to slowly decrease the back pressure starting from equal to P naught value. Okay. When we start with Pb equal to P naught, we are going to have no flow, and when I slightly decrease the pressure there, immediately the pressure differential will drive the flow, and when the flow starts, we know it is going to be subsonic because it was stagnant just before this. It will be subsonic, and subsonic flow convergent duct, it will increase in area, increase in velocity, that is going to increase in Mach number, and after that it will still be subsonic. I said it is a very small pressure differential, it is not going to get to sonic condition here, and after that it is again going to go subsonic and lesser lesser subsonic value, lower Mach numbers it is going to reach finally. Okay. And if I look at what happens to pressure as a function of distance, we know that from here to here the flow accelerates and P naught is maintained constant and it is very low subsonic values. We can even think about it as Bernoulli's problem, Bernoulli's equation, and we can tell that when velocity increases, pressure decreases. But even if I think about compressible flows, when Mach number increases, pressure decreases. For isentropic flows, we are still using isentropic flow. So, I am going to get something like this, okay, from inlet condition to the throat condition. I am calling it throat, I am not putting a star on top of it, only when I put star it is choked condition. From here again I am having subsonic flow and it is diverging duct, so my flow decelerates again and it is going to some other value. Now I have to be very careful about what will be the final value compared to the initial value. Initially I am going to say this is close to my P0 stagnation condition, and the final value cannot be equal to P0, it has to be slightly less, otherwise there is no flow. Okay. Just be careful in drawing these pictures, that is it. This is the particular Pb value we are thinking about, and after that the pressure is the same. To maintain that pressure only, there was this flow going through this nozzle. Okay. That is the situation. Now if I pick up, let us say this is my P naught, I will draw a dotted line here. If I pick a slightly lesser Pb, say this value, then my flow accelerated a little more, it will start from the same, going to go to a lower value, and then it is going to go here. Okay. I am showing all this really nicely. We have to know that the scale of this, I have not put any numbers here, all these will happen really small values. Okay. Now depending on whatever is my Pb to P0 ratio, the final pressure in the middle will be decided. Okay. So to decide this problem, what matters is just this ratio of Pb to P0, or we can say that it matters only if I think about P0 and Pb, these two numbers, that is what matters for this problem, and typically we write it as P back divided by stagnation pressure. This ratio decides this problem. Okay. So let us go to the screen. I am showing here the nozzle which I have calculated the pressures for. I am showing you here A by A star, where star is the throat condition here, where it is 1, A by A star is 1 at this location. This number does not mean anything really, the x axis is just some distance. Okay. You are going to see that it is starting from A by A star of 5 and goes to A by A star of 1, and then it goes back to 10 at some location. Okay. Even if I stretch this nozzle along the x axis, the flow will not change except for the plots will also be stretched along the x axis. That does not mean anything for us, we will not worry about it for now. Okay. Now, if I look at the Pb by P0 value, I have to show you what the plot is. It is pressure divided normalized by P01, that is the initial stagnation condition somewhere far outside. Okay. And from there we are plotting for different locations, as if I am having pressure measurement along this nozzle all over. That is what I am plotting here. If there is a small change, then this throat section is going to have a pressure of 0.99. I am thinking about 10 power minus 1, 10 power minus 4 drop from 1. Yeah, it is a very small change in Pb by P01 value, and that is giving you a 0.99 P by P0 at the throat location. Okay, but if you look at all the other places, most of the other places it is almost 1. Okay, it will probably be ending in 0.9999, that is what it will end up with. If I go to a 0.9996, then I am going to have much steeper drop, it is going down very fast up to here. Okay. And I just wanted to zoom into this region. So, you are seeing that from 0.9999 to 9996, it has dropped from 0.99 at the throat to 0.946 or something at the throat. Okay. It is dropping more seriously, and I make it 9990, it is going even below 0.9. Okay, I have not shown it very clearly here. Okay. And if I keep on doing this, I decrease it by a small amount, there is a point where it becomes choked at the throat. That particular calculation happens to be happening at 0.9976. This happens to be your first critical pressure. Okay, we were discussing critical pressure. This is the point where the throat location is first choked. I am slowly decreasing my Pb and it is getting choked at that point. Okay, we will go deal with numerical example probably another day, maybe next class. As of now, we will just assume that this is what happens. We will calculate how to, we will figure out how to calculate these numbers and these plots some other time. Okay. Now, once we understand this, we can proceed further. I will go back to the board and extend the plot further below. I will extend the plot further below. This is again my location x. And I said P here we are normalizing it to P0, we will keep it that way, in which case this will become 1, that is it, no difference. Pb by P01 is what I am changing. So, I have decreased and there is a point where it is critical. Let us say this is my P star value. So, this is my star condition. From here it is going back to this is my P critical 1, P critical 1 divided by P0. Since we are plotting ratios here. Now, after this we said that the flow wants to be supersonic, and if it is fully supersonic, I will draw that curve also. If it is fully supersonic, then at the exit the pressure will be very, very low. This is your critical 3, we said, P critical 3 divided by P0, that is what I have put there. And anywhere inside the flow is not fully isentropic flow, we said. Okay. So, what we want to do is, if I go through the process of starting from Pb by P0 equal to 1 and going down slowly, I will go to a point where suddenly the flow becomes supersonic partly, and then it realizes that it cannot reach that pressure. So, it goes through a shock, becomes subsonic, and then goes on a subsonic line. We already know that if it is subsonic flow and then diverging duct, it is going to increase in pressure similar to these curves. We already have subsonic solutions. Now, this is what the flow does. Once it is below critical pressure 1, it is going to take the supersonic path for some time or some distance in this case, and then it is going to jump across to subsonic solution using a shock, non-isentropic flow again. Only this one spot is non-isentropic really, just that one region. everywhere else it is isentropic. From here to here P01, and after this it is P02, really, right, because there is a drop across this shock for P0. Okay. But the way we plot it, typically we normalize even the other curve, the pressure downstream, also with respect to P01. That is where we have to be more careful and say P divided by P01, so that in case of the shock being existing, we have to be very clear which P0 we are using. Okay, if I use P02 here, that curve will be slightly different. We just want to keep single normalizing factor, that is P01 for us. Okay. Now if I go for even lower pressure than this value, let us say somewhere in here, then that will take supersonic path for even longer time, jump up to a subsonic solution, and from here it is going to go reach that value, something like that. It is going to pick some such solution. You should know that the P2 by P1 jump is going to be higher and higher as it goes down here. Okay, that is also true. Why? Why is that? Why will the P2 by P1 be higher as I go along x? Mach number is higher because when I go from here, throat is choked now. If it is choked, then I am having, if I have pressure very low, I have to always give this constraint. If the flow is choked, I cannot tell for sure what the downstream Mach number is unless I tell you the downstream pressure. Now we have decided that the downstream pressure is below pressure critical 1, which means the flow just downstream of the throat is supersonic. Otherwise it can never reach that. That is what we saw. It will take this particular path if it is fully subsonic, that will not reach any of these values. So it will take a supersonic path up to some particular location. Let us say we will talk about this particular curve. Somewhere here there will be a shock, till here it is m greater than 1, after that it is m less than 1. Okay. At this location it is non-isentropic, only this one spot. We already discussed that shock is a very thin layer, and we will assume that it is a point change in my full x dimension. So up to this point the flow is supersonic, and from this point on, at this point it jumps from supersonic to subsonic, and from this point on it is subsonic this side. That is how we will deal with this problem, simple enough to deal with. And once we know that it is subsonic, after that the diverging flow will increase Mach number, decrease Mach number, further increase pressure and go to meet the correct PB value. If I decrease the pressure further, then the shock goes more out. Okay. The shock goes more out. What does that mean? Now my flow, if the shock goes more out, the shock sits at a higher area. Higher area means from throat m equal to 1, I have become supersonic and it is diverging duct, it is going to increase in Mach number much further, go to a higher Mach number here, and so the pressure drop will be higher. Pressure jump will be higher, not a drop, it is actually increase in pressure across the shock. Now let us think about this and give a physical feel for this. I decrease pressure here, why should the shock go more out? Just from physical point of view. Not understanding. Pressure needs to get higher. I am not going to think about it that way. I am thinking, say I was already operating at this shock location, and from here I want to go here. Okay. Say my shock was initially here. I decreased pressure and the shock went here. Decreased back pressure, keeping P0 the same, and my shock went more downstream. Can we give a physical feel for this? From here to here, yeah, I am going from here to here, pressure is decreasing at the exit, that is what we are looking at, pressure is decreasing at the exit. And why will the shock go more downstream? Mach number comes only after the shock moves, till that time it is the same Mach number. Why will the shock move is my question. The way I am going to think about it, why will the shock move? What is that? More freedom to go. Okay, let us think about it slightly differently. That is probably one way of looking at it. We had this other example in flow in a duct, constant duct with with a single shock sitting at a particular location long time back when we introduced normal shocks. Okay, stationary shock moving flow we said. The way we thought about it was the shock had its own speed and that was matched exactly with the flow speed, and so it was standing there. It is a nice way of thinking about it. We said that it is as if this flow is like a treadmill and the shock is running on top of it and it is equal speed, so it is maintained constant, right. That is nice to think about it. Now suddenly if I send an expansion wave from here, what will happen? This is an expansion wave, this is actually a shock. What will happen if I send one expansion wave? This subsonic flow, it will go against it and reach it. When it reaches, what is shock? It is really a bunch of compression waves together. What will happen to it? All the compression waves, the last wave alone will be negated by this expansion wave, right. There are so many waves, let us say there are 100 waves inside that shock. I sent one expansion wave inside, now it is only 99 waves, it is not 100 waves. So what will happen? That moving shock is now going to go slow because not so many compression waves, one wave less. Okay. So what will happen? Treadmill problem, easy to understand. What will happen? The treadmill speed remains the same, but the guy running against it is running slower, so he will go that way. Okay. Now we will go back to this problem, apply the same logic here. I am going to say there was some particular back pressure when the shock was here. Now I decreased the pressure here, the flow was subsonic downstream of the shock fully. This whole region, it was all subsonic, right. Now since I decreased pressure, that change always causes a wave, right. The stadium, we changed the gate, the flow changes a wave, right, there is a wave goes through. So that decrease in pressure sends out an expansion wave all the way through, and by the way if you change it too suddenly and you are doing high speed imaging, you will see that that wave will travel through all the way. Until that time the shock will not respond to that, till that time of propagation of the wave this shock will not respond to it. Okay. Now we will assume all that is just high speed flows and unsteady stuff are not present current world, because we are thinking quasi steady problems. We are making changes but we wait for infinite time after that. We will not worry about what is really happening during the unsteady motion. Okay. So I am going to say I decreased the pressure downstream, so there is an expansion wave coming in and weakening the shock which was originally here, and because of that the shock is being pushed by the flow more downstream. But as it goes more downstream the Mach number changes, and because of that the shock finds a nice place to sit. Okay. It goes there, shock becomes stronger and stronger, and the Mach number of the shock gets higher, it can run faster. But remember the flow is also getting faster, it will go and sit at a new point where it is going to be equal. Okay. That is where it sits. If I decrease too much the shock will go more out. Okay. This is one nice way of thinking about it. This kind of expansion and compression waves moving around helps you a lot in understanding and getting a physical feel for the problem. Okay. So I have got to this point. Now if I decrease further, what will happen? Again another expansion wave comes through, makes this shock weaker at this particular location, it will go more downstream. Okay. I keep on going like that. Say I reached this point, there will be a point where the shock will go to the exit, and just outside it is meeting the correct pressure, and that we said was P critical 2 by P naught 1. Okay. I am again being very careful in marking P naught 1 always. Okay. That is our normalizing factor. There could be a P naught 2 in case of non-isentropic problems where there is shock sitting inside my divergent duct. It does not matter for P critical 1 or 3, but anyway just for consistency I just put P01 everywhere. It matters mainly for this other cases where there is a shock sitting. So if this is the problem, now there is a shock at the exit, and immediately after the shock the flow is meeting the pressure that is outside, it is all matched perfectly nice, it is just going to sit there. So the full flow inside, now we are at the exit, shock at the exit, I will rearrange this again, shock at the exit, I am going to assume 1D flow, so the flow is going to go straight here. This region there is a shock, here it is m greater than 1, in fact m equal to m exit at that shock location, and I am going to have subsonic flow just after the shock, and the pressure is matched, P exit is equal to Pb. If you notice all these cases up to P critical 2 back pressure will always be matched. Okay, back pressure can always be matched. There will be a point where when I go any more outside, the shock, if I decrease the pressure further below this P critical 2, the shock will be pulled out further, okay, or the shock will be pushed out by the flow. That is another way of looking at it, right. We said the treadmill business, shock will be pushed out by the flow a little more. Okay. We will go and study that after finishing this nozzle flow problem. We will study what happens just outside a nozzle that creates a jet flow. The next thing in our agenda is jet flows. Okay. Once we finish this, we will discuss what happens outside this part. Okay. Let us just go through this problem currently. As of now, we will just say that the region between P critical 2 and P critical 3 is a region where the nozzle has a P exit that is less than the PB value. That is, the nozzle has expanded the flow more than required. Okay, that is over expanded case. The pressure is too low compared to what is needed. It did not meet the back pressure. Till here it met the back pressure. Here it does not meet the back pressure. So this is your over expanded region from P critical 2 to P critical 3. At P critical 3 it is perfectly expanded, fully supersonic flow inside the nozzle. I can even say that from PB equal to P naught till PB equal to P critical 2, my flow is perfectly expanded because it meets the back pressure, right. But typically when people talk about CD nozzles, they just talk about fully supersonic flow inside, and they just talk about from below P critical 2 onwards when they talk about over expanded, perfectly expanded and under expanded. Even other places, even above P critical 2, everywhere I am matching the back pressure exactly. P exit, P at the exit matches the P back pressure, PB. Okay. But this region is our over expanded and this is your under expanded. This is what you will have. Okay. So this is just explanation. Now I go back to our nozzle plots which we had. All this time we plotted only up to above P critical 1 values, what we saw before in plot. I will go back to the screen. We will look at remaining plots. Okay. We will look at this particular plot where it is again A by A star, it is the exact same nozzle I am picking, and I am having this as a distance, same thing here, distance, and P by P naught 1. Now I have to be more specific, P naught 1. Okay. And all the previous curves I showed, they are all here, this region. In fact, I showed you the dotted line also, which corresponds to that 0.9976 number. Okay, that is also matching here. After that, you can see what PB by P naught 1 I used really, just directly from here. I used 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1. Okay, actually, I used this number slightly above 0.1. I think it was 0.13 or something for this particular nozzle, gamma equal to 1.4 case. Okay, that is the second critical pressure. So if you see what is happening, I have plotted for a linear nozzle, straight line nozzle. It's this curve does not change beyond that point. The subsonic part does not change. Why? Obviously this point gets choked, and whatever downstream happens, nothing gets affected in the upstream of that Mach 1 condition. This is choked condition, nothing upstream changes beyond that point. So this curve is the same for all these curves, starting from this red dotted line all the way till all these curves to the left of x equal to 1 is all the same. Every curve is one on top of the other. After that, I am going to have different curves. After that, if I pick this PB by P naught 1 as 0.9, then it goes through this up to here. The shock is sitting at this location, and from there it is jumping to some other pressure and it is going through this, okay, going through the remaining part as subsonic solution. And you can see as I decrease my back pressure, the shock is going more and more downstream. These vertical lines correspond to two pressure values at the same location, which basically means that I am having a shock. Okay. So it just jumps and keeps going like this, and the shock goes all the way to the exit. Now I will ask you a nice question here. If I look at this particular case, it looks like the delta P is really high here, while for a higher Mach number the delta P is lower, and even at the exit, which is supposed to be the highest Mach number for the shock, it is the lowest delta P. Is that logical? Let us look at you guys. Is that logical? Yes.
Shock is moving.
Yes, shock is moving one case to the other, but the delta P seems to be getting lesser and lesser. Is that logical? Delta P in this case happens to be P2 minus P1 for each across the shock for each of those cases. It seems to be lesser. Is that logical?
What about the back pressure?
Back pressure is continuously decreasing, which means my strength of my shock should increase, right? That is what we have been discussing till now. In fact, the Mach number at the shock is higher. We are seeing that the delta P is lesser, and I know for sure there is nothing wrong in my calculations. Is that logical? Can we explain this? Is the basic question. When we say the strength of the shock, what do we mean by the strength of the shock? Strength of the shock increases. That is where the answer lies. What is that?
To what extent it can make the flow subsonic, in the sense?
Up to what extent it can make the flow subsonic?
Velocity difference.
Clear. Probably you are talking about the Mach number jump, the delta m you are talking about.
Yeah.
We will look at that. The next plot I have is delta m based plot. This is pressure versus distance. Now I have a Mach number versus distance. We will hold that for now. Maybe you are right. Pressure based answer is what I am looking for. Okay. So, it so happens, we will go to the screen again. It so happens that from here to here there is a huge pressure jump. I am at say 0.24 or something, it is going all the way to 0.67 or so. And here if I look at it, let us find the number, say 0.25 and 0.68 or something like that. It will be of the order of 2.3 or so, P2 by P1. Let us say I go here, I will pick a nicer number. Let us say I will pick this one, this is 0.1 to 0.5, P2 by P1 is 5. Okay. All this time we have been talking about pressure, the pressure jumps, but what we really wrote on the board for strength of a shock was really P2 by P1 at that Mach number. This is the strength of shock. Really the strength of the shock increases for that Mach number. Okay. In fact, you can see that in the plot also. Already I gave you two numbers. One of them was 0.65 divided by 0.24 and the other one was 0.5 divided by 0.1. This is at a higher Mach number and this is going to give you an answer 5. This is going to give you something 2.3 or something, some such number. I am not just generally calculating, it is something between 2 and 3, that is all I know. It is of that order. Okay. So, you are already seeing that P2 by P1 has increased from there to here. Okay. So, it is matching with whatever we have been discussing till now. The strength of the shock increased, but what I mean by strength of the shock is only P2 by P1 and not P2 minus P1. If I look at P2 minus P1, this is actually P1 multiplied by P2 by P1 minus 1. This is what it is. Okay. It so happens that this number increases, but I am multiplying by a very small number. P1 keeps on decreasing with Mach number increasing. Because the shock goes to higher and higher Mach number, the pressure on the supersonic curve, we will go to this plot, I can even go to the screen, but this is better. When I go along this supersonic solution, my pressure keeps on decreasing. So, at every shock location, the P1 which is just before the shock, that pressure is decreasing as I go more and more downstream. Okay. That is why it looks as if the plot in the, let us go to the screen now. If I look at this plot, it looks as if the delta P is lesser. Yes, delta P will be lesser, that is primarily because the P1 itself is really low. From that low value jumping up to that high value is an enormous job done by the shock. Okay. If I think about this particular case, it is probably 0.1 going to around 0.18 is like 18 times increase pressure, while at this particular condition it is roughly 0.1 going to 0.5, that is 5 times increase. Okay. Pressure has been increased by 5 times roughly here around 18 times here. So, it is increasing much more, while it was the very first curve we had, it was around 2.4 times or so. So, it is increasing drastically, okay. That is what is really the truth. Now, we will go to the next plot. We had this Mach number discussion anyway. This is the Mach number plot, okay. Now, whatever she was talking about is actually true, right. The strength of the shock is actually related to how subsonic can it take the flow, if you think about it that way. Actually, let us explain this again, the same nozzle plot above, A by A star versus distance along x axis, and here I am plotting Mach number at every location versus x axis. For the same set of Pb by P01 I used to plot in the previous case, okay. If you look at for very low Pb by P1 values, very close to 1 values, all the curves are here, it is going through fully subsonic solution and then it is going back to low subsonic. It increases closer to sonic, goes back down to low subsonic. There is a point where it becomes sonic and then goes through this path. That dotted red line is our P critical 1 pressure P back, okay. If I go anything above that, anything below that pressure, my Mach number increases, it goes supersonic, jumps across the shock to subsonic. So, you can see that m equal to 1 line is here, it is jumping across from there to here to subsonic, and then it is going subsonic solution, decreasing Mach number further. If I decrease pressure further, it is going to go to even higher Mach number, and then from 3.5 let us pick, it is going to drop to 0.4 or so, it is dropping really high, while in the initial cases it is something of the order of 1.6 to 0.7 or so, rough numbers, okay. It is jumping only a little bit, and when I go to the highest case I have, that is probably 3.9 dropping to 0.4 or so, something of that order, okay. So, it is dropping really huge amounts, which means the shock strength is high. That is her way of giving the definition, right. We got one definition from here, which was a shock is considered to be stronger if it starts from high Mach number and drops to really low Mach numbers. How low can it go in Mach number? That is one way of thinking about shock strength also, that will also work, okay. That is this picture. Now, I want to go beyond what is given in ordinary books, and I think I wanted to show you one more before that, an animation. Okay. This is the same thing, just I have added animation of pressure color coded. Red is high pressure, blue is very low pressure, and green is somewhere in the middle. So, what you are seeing is very high pressure, coming to some green is your throat condition, choked, and then it is going subsonic and the shock is moving as we go. This is what really happens inside your nozzle. We saw a movie of this from an experiment, I think last class or the class before anyway, okay. We start with fully red, which is almost no flow, and then it is becoming more and more low pressures, the center becoming supersonic, that blue is all supersonic conditions, very low pressures, and the shock, this jump is the shock really, and that is moving more and more downstream, okay. This is one nice thing. We can of course plot other things like temperature, Mach number, everything similar, they all look the same almost, okay. Now, I want you to think a little beyond this. I want to look at the same nozzle problem. I am going to keep back pressure fixed now, okay. This is my exit condition, this is my throat condition, this is my inlet, and there is a big tank here which will be my P0. This is our standard model for our nozzle flow, right. Now, I am going to say that I am keeping my back pressure fixed. Let us say the nozzle is exiting into atmosphere, atmospheric pressure does not change so much, okay. And I am going to have a big tank. Now, the tank is being pumped in, compressed more and more, there is more air pumped into this tank as we think about it. So, if P0 increases, what happens to this nozzle? That is the other question we are going to look at. I will tell you one simple answer. If I plot it as P by P naught versus distance, the plot does not look any different, it looks exactly the same. This is the reason why most books give you this plot. Okay. It does not matter whether I keep P naught fixed and vary Pb or keep Pb fixed and vary P naught, this plot does not change. Okay. That is the important thing there. So, most of the books will tell you this P by P naught plot as a function of x, and they will just talk about one particular case, which is keeping P naught constant and decreasing Pb. Okay. And this gives the wrong impression that if I keep on changing back pressure only, I will have my Mach number go downstream, okay, my shock go downstream. That need not be the case. Okay. I can even have the opposite problem. If I want to decrease my Pb by P naught, let us say that line, right, we used to draw this kind of plots, that line can be decreased by increasing P naught, keeping Pb the same. Even if I do that, that will drop to some other value. Okay. If that is the case also, you will again go through the same set of plots. Okay. But it is more fun to look at this plot as just pressure versus x. It is more fun to look at the plot that way. It gives you a little more insight into what is happening in a duct. Okay. Let us go back one step. What if I do the same thing here? Instead of plotting P by P naught, I just plot pressure versus x. What will this plot look like? It will not look any different because I am just dividing this whole thing by a constant, that will just change the scaling, does not change anything else. Okay. If I multiply this whole thing, this whole every plot, every point on the plot by a P naught 1, that is just equivalent to multiplying this 1 by a number P naught 1, and similarly if it is say 0.8 P naught 1, 0.5 P naught 1 for gamma, right, gamma equal to 1.4, it is 0.53 something. So, it is going to be 0.53 of P naught 1, that is all, nothing changes, it just scales this plot. That is not the case when I change the denominator. So, I will go and plot it again, I will just plot pressure versus x in this case. Okay. If I do that, the first thing we have to say is I am fixing my P atmosphere or my back pressure. This is always, I want to call it back pressure and not exit pressure for now. Back pressure, that is a fixed value in my whole system. I am starting with this P naught and I could decrease it. If I decrease it, it is reverse flow in the nozzle, we will not consider that case, it is silly, we will just go above this. If I go above this, we know that from P naught the pressure decreases and then increases to Pb, which means it should do something like this, it will go below and above, right. So, if I think about it like this, what have I done from the previous plot? Let us say it was this case, this particular curve, let us pick, say I had that particular Pb divided by P naught as the other curve there. What I have done is, I have multiplied this curve by a P naught such that this curve has been scaled up a little bit and this point has been made to reach this dotted line. Okay, because Pb is a particular value, we are fixing Pb. So, it has been made to reach this dotted line, that is all I have done, it just came here. Similarly, if I increase it further, we know that it is going to go drop more and then go back up again to reach the same Pb. And let us say this is the point where I get the star condition. So, this will be my P naught critical 1. Now, I have to call it P naught critical 1, not Pb critical. Okay. That is the difference because I am doing the opposite experiment. Okay. I am not changing Pb, now I am changing P naught, that is the main difference, and it is going to go through this path. This is what I will get. Now, of course, I can keep on doing this further and you will see that oh, there is one more thing I want to talk about. If I increase P naught any further, the choked condition remains choked. What happens to the P star, the pressure at the throat? P star, will it be the same? I am increasing P naught, so P star should increase. Why? P at throat is equal to P star, which is equal to P naught 1 into P star by P naught 1. We know that this is a constant. This happens to be your 0.528 for gamma equal to 1.4. That multiplied by P naught 1. So, P star should increase. Okay. So, if this is my critical pressure 1, the next case is going to be higher, and then we know that it's, if I go above pressure critical 1, Pb by P naught will go below my first critical pressure, which means I am going to go supersonic, jump across with a shock and go subsonic. So, it is going to go like this, jump across and then go along to subsonic solution to reach that back pressure. Okay. It looks more confusing beyond this point. Let us go to the screen again. We look at this particular picture where I am having the same nozzle. I have just plotted it differently now. We are keeping the exit pressure exactly the same as the back pressure, and the flow wants to meet this pressure whatever happens. What we are saying is, it starts with slightly higher value, it goes down and goes back up, it is all merged inside here, you cannot see very clearly. But say about 2 or so, it is going to go become supersonic, have a shock and then go through the subsonic path. And as I increase my P naught, now my shock is pushed more downstream. Now I go back to my shock and expansion explanation again. We will go to this picture. I am going to say that there was a shock, pressure here is exactly the same, but here I am increasing pressure. What does that mean? The flow strength has increased. Okay. So, the treadmill is running faster even though the shock does not want to change its strength. This is the opposite way of looking at it. Okay. Treadmill is running faster even though the person does not want to change his running speed. He is still running this way, shock is continuously trying to run against the flow, and the flow is matching it if it is staying constant speed, constant location. But now I am increasing P naught, the strength of this flow is higher, it just runs through. Okay, it is like a stampede, right? When there is a lot of bulls running through and there is some shock trying to run against it, it is not going to happen, it is just going to go through that way, and it goes to some other location, and where this will match nicely. Till that time it will just keep going this way. Why will it match nicely here? Suddenly the shock strength is increasing, area is changing, shock strength is increasing, it is running a little faster, and the flow strength will decrease because the pressure here is decreasing. So, they will come to a nice compromise here and they will sit at that point. That is how it goes to the new point. Okay. And of course, beyond that point, this we go back to the screen, beyond that point I do not want to plot too many functions here, it will just make this just get crowded. Okay. I have drawn one case here and the one case where shock is almost at the exit. Okay. You can keep on drawing this forever, and I have drawn the completely perfectly expanded case here. That is your dotted line here, where we are seeing the pressure for it to meet will be somewhere way high above the screen probably, and it is going to come down and go down like this. If you look at this x equal to 1 location, which is our throat location, the pressure is continuously increasing after it gets choked. It is continuous, in fact even for some time it will be decreasing and then it will keep on increasing above that. It will keep on increasing. At this point this is the pressure P star. If you look at that number, from there it will be roughly half. 0.75, half of that is 0.375, it is slightly more than that. So, it will be, this is my x equal to 1 point, P star is higher, it is above atmosphere here, P star. Okay. If I do this particular experiment of keeping my exit pressure fixed, back pressure fixed, not exit pressure, back pressure fixed, and I increase my P naught on this side, then it is going to keep on, it will decrease my P star for a little bit and then it will keep on increasing my P star because my P naught is increasing. Why will the pressure at the throat decrease for initial cases? Initially it is subsonic, where there is very first case it is no flow, so pressure is same as atmospheric pressure. After that it is some flow, but it is all subsonic, it will go below and then increase to atmospheric condition. That is the reason it is going to decrease initially. From there it will decrease, after that all the curves will go up. Only if you plot it better you will see it nicely. I will just show you an animation instead. This is the other animation. Okay. This is the other animation where I am plotting one by one in each of these. This dotted line of red corresponds to the P critical 1, this dotted line of red corresponds to P critical 3. Okay. And as this pressure increases, you can see that the shock is formed and it is moving more and more downstream. I am plotting one at a time, and this is showing you the same thing with pressure. As the pressure increases here, the shock is being pushed out slowly. Okay. That is what this animation is supposed to show you. Okay. This just gives you a feel for what is happening in there. Okay. So, now we are at a point where we can move on to something else, but instead I am going to talk about how to calculate these, okay, how to calculate these pressures and Mach numbers if I am given a particular nozzle geometry. Given a nozzle geometry and given a particular P0 and a particular Pb, how will I find the pressure distribution along distance? That is what we want to do next. Okay. And there is not enough time today. I will just give you the subsonic thing, very subsonic. Pressure Pb by P0 greater than P critical 2 by P critical 1 by P0. This is very simple case. We know for this particular condition, flow is always subsonic. Okay. Flow is fully subsonic, easy to calculate. I know my area here, okay, and I know it has to reach this pressure finally. I know my P0, I will find Pb by P0 here, it will match the pressure. So, it is going to give me my M at exit. Once I know M at exit, I can use M at exit will give me my AE by A star. Mind you, A star need not be same as A throat because it is not yet choked. Okay. So, I will find my A star for this particular flow. Once I find that, I have different areas in this nozzle. All I have to do is find this A star and go and take any particular area. A by A star will give me my M at that location. Once I know Mach number distribution everywhere, I can find pressure everywhere. Why? I know my P naught, so I can get from my isentropic tables for the given Mach number I will find the pressure. Okay. This is a simple way to solve this problem. Okay. We will deal with the other cases because it needs iteration. Okay. The remaining cases we will deal with later.